Special Agent Flammable here. I'm sneaking across the chalkboard. I was pretty invisible to ya guys, my boys. No, I wasn't. Last video on this integral right here. We are going to solve it using complex analysis today. I guess you guys were waiting for this method. So, just like with many other trigonometric functions, it would be nice to integrate it over the upper half of the complex plane. So at first, let's define some new complex function, f in terms of z. And we are going to define it as follows. This is e to the I z over z squared plus 1. You will see why I'm doing this in a minute. Okay, but we can rewrite this. I hope you can see that this positive one is nothing else than I squared, but with a negative sign. So that makes the difference of two squares, and we can factor this. So we have e to the I z over, and we have z plus I and z minus I. And just like I said before, we want to integrate it over the upper half of the complex plane. Let's take a look into the complex plane. So we have the semicircle right here, and it goes from minus r to r. And also we have some curvy boy gamma up here. This is our contour C. And we want to integrate it over this closed contour. So let's do this. We are going to integrate our f in terms of z, dz, over this closed contour C. But what does it consist of? Well, at first we have this curvy boy gamma. So we have our gamma integral and plus this integral from minus r to r. But as you might notice, we are walking across the real axis right here. That means we can also write it as f in terms of x dx. Okay, nice. But don't forget, we have this right here, and we have to take a look at the residues. And now we need to take a look for the poles. So one pole is at minus I and the other one is at I. But in our contour, only I is in here somewhere. Okay, so that means we need to take a look at the residue at the point z equals to I. That's Cauchy's residue theorem. So we have that this contour right here is just 2 times pi times I times the residue when z equals to I of f in terms of z. Okay, let's take a look at the residue. The residue, z equals to I, at f in terms of z equals to. So we have a single pole right here. That means we are getting rid of this derivative stuff in the residue. And all we end up with is the limit as z approaches to I of z minus I times f in terms of z. But what is f in terms of z? It's just e to the I z over, and now we have this right here, this denominator z plus I, z minus I. And the great thing is, this and that we cancel out, and now we can let z approach I. That means we get 2i down here, and we have I times I is just minus 1, so that's e to the minus 1. So now we have 1 over 2 times I e to the first power. I'm bringing this in the denominator. So we now know that our contour is nothing else than this sum of integrals right here. And it's nothing else than 2 times pi times I times this term right here. So let's plug everything in. That means we have our curvy boy plus our real boy, f in terms of x dx, and it's now equal to 2 times pi times I times 1 over 2 I e. This and that we cancel out, so we end up with pi over e. And you might recognize this result from the last 2 videos. It's going to be the result to our original integral. And that's quite nice, because this e to the iz will give us information about the cosine and the sine, because this is just Euler's formula, which gives us cosine of z, in this case, plus I times the sine of z. But we are walking across the real axis right here, so we are going to end up with some real valued sine and cosine, which is this right here. So all we need to do is we need to let r approach infinity. That would give us our original integrand, kind of. And we need to show that our gamma integral is going to vanish when r approaches infinity. And that's what we are going to show now. So let's take a look at the curvy boy gamma. So we have this integral gamma of f of z dz. We need this z now because it's along the imaginary axis. Okay, now we can plug everything in. From where to where does this go? Well, it goes from r to minus r in this case. So we have an integral from r to minus r of e to the iz over z squared plus 1 dz. And now we want to introduce a natural parameter. So let our z, for example, equal to r times e to the I phi. That means if we differentiate that, dz is now going to equal to I times r times e to the I phi d phi. And now we can plug all this information in. So this is now equal to the integral from upper and lower bounds. If we plug r into here, that means r equals to this chunk. We can cancel out those r's. That means e to the I phi has to be equal to 1. So we need to find the right value for our phi so that it equals to 1. Well, if we plug in 0 for the cosine, that would give us 1. And the sine of 0 is just 0, so that is great. So this goes from 0 to, if we plug in minus r into here, that means e to the I phi needs to equal to minus 1. That's something that's well known. We just plug in a pi into here. Whew. Okay, and now all the rest. So that's e to the I times r, e to the I phi. That's a weird exponential function. And also we have r times e to the I phi plus 1, but this chunk is going to be squared, and we also have our dz, which is I times r times e to the I phi d phi. Okay, great. And now we need to show that this goes to 0 as r approaches infinity. How are we going to do this? We want to find some upper or lower bound. That means we are going to take the absolute value of our gamma integral. So that's what we are going to do at first. So we are going to take the absolute value of this thing. That means we have to use the triangle inequality. That means the direct path is shorter than some detour. That means that's less or equal to the absolute value of. And now we can distribute everything into everything. So if we just apply the absolute values here, it's still going to be equal, but if we apply it to every part of this function, it's going to be less or equal. So at first we can bring this to the outside, so we have the absolute value of I times the absolute value of r. Quick little spoiler, r is going to be strictly positive, so we are getting rid of this absolute value, and the absolute value of I is just going to be 1. So that's quite nice. Now we have the integral from 0 to pi. And the next step, so we have the absolute value of e to the I r e to the I phi over the absolute value of r squared e to the 2 I phi plus 1 d phi. And now we need to take a look at the numerator and denominator. And I want to take a look at the denominator at first. So we have the absolute value of r squared e to the 2 I phi plus 1. There's something that's called the reverse triangle inequality, and most of the time you are just going to need it in cases like this. This inequality tells us that this is greater or equal to. There's one condition that we need to meet. There needs to be a minus here, so we are just going to turn it into a minus 1, which will give us positive 1 in the end. This term is greater or equal to the absolute value of r squared e to the 2 I phi, and then minus the absolute value of minus 1. The absolute value of minus 1 is just going to give us 1, so that's nice and fine. And also we can use the multiplicativity of the absolute value, and we can distribute it into here. E to the I times something, when the something is real, is just going to give us 1. So that's a nice identity. You can easily check on that. And, well, r squared is always going to give us positive values. So let's get rid of that. So we have this now, so we have the absolute value of r squared minus 1. And remember, we are going to make r arbitrarily large and huge. That means it's going to be positive, and infinity, positive infinity, minus 1 is just going to give us something that is positive. So in the end, we are getting rid of those absolute values, so this is r squared minus 1. And now we can take the reciprocal on both sides to turn around this order relation. Because we need a different order relation. We need this right here to be less or equal to something. Okay, so that means we have 1 over this chunk right here, this term, is less or equal to 1 over r squared minus 1. So we can check on all of this. We've got the right order relation, and we have got rid of this absolute value. So that's nice, we can plug this in, and now we need to take a look at this right here. How can we manage to work with that? Well, at first we can make use of Euler's formula to transform this right here, kind of. So we are going to rewrite this as the absolute value of e to the I times r, and this is going to be the cosine of phi plus I times the sine of phi. Okay, nice, and don't forget your absolute values. Now we can distribute this I times r into everything, and what we end up with at first is the absolute value of e to the I r cosine of phi, and then I times I becomes minus 1, and also we can use the fact that we have the same base and we can break this up into another exponential function, make it multiplicative. So we have e to the minus r times the sine of phi. Okay, once again we can use the multiplicativity of the absolute value to break this up into two absolute values, the product of two absolute values. Okay, great. And like I said before, e to the I times something when the something is real, and both r and the cosine of phi are going to be real, is going to be just 1. So right now we would end up with the absolute value of e to the minus r times the sine of phi. And all we need to show now is that this is less or equal to something. And we can make use of the fact that we are just walking along the upper half of the complex plane. That means our angle phi is going to be from 0 to pi in this case, and that's pretty nice. So let's take a look at the graph of sine in the interval 0 to pi, and you might notice the sine is just going to be positive, so that's nice. So we would end up with e to the minus r, no? Because positive and minus won't change anything. The sign will be the same. And also don't forget, e to the minus something when the something is real will leave us with some positive value, so we can naturally get rid of those absolute values. I forgot that. So how can we find an estimation? Well, we have e to the minus something, and r is getting arbitrarily huge. That means this is going to be qualitatively less or equal to 1. So that's our bound for this function right here. And now we can conclude that this whole term right here, this estimation is just, and it's going to be less or just equal, it doesn't matter, r times the integral from 0 to pi of. So this is just going to be 1, and this is going to be r squared minus 1 d phi. Well, great. And now we want to let it approach infinity, the limit as r goes to infinity. Well, you might notice r squared minus 1 is going to dominate r. Or you could factor out an r in the denominator and numerator, and you might notice that this is going to go to 0, this first term, and the integral from 0 to pi of d phi is just going to be some real number. So this is indeed going to 0 in the limit as r approaches infinity. Okay, great thing. Now we've got all the information that we need. That means the limit as r approaches infinity of our contour integral of f of z dz is nothing else than, okay, gamma is going to vanish, and we know what our residue was, so it was pi over e. Okay, and it's not affected by the limit, it's independent of r. And now we are going to let the limit as r approaches infinity of this integral from minus r to r of e to the ix over x squared plus 1 dx. And indeed, we would end up with the integral from minus infinity to infinity of e to the ix over x squared plus 1 dx, which is basically our original integral, but we still have this up here. So we can break this up into two integrals because it's Euler's formula. So we have the integral from minus infinity to infinity of cosine of x over x squared plus 1 dx, and then positive. So we can bring this I to the front, the imaginary part. So we have minus infinity to infinity of sine of x over x squared plus 1 dx. And this right here is real. You might notice it doesn't have an imaginary part. It does have one, it must have one, because that's a complex number, but the imaginary part is bound to be 0. And it does make sense that this right here is just 0, because if you plug in minus x into this integrand, you might notice we would end up with the negative integral of this right here. So this right here is an odd integrand over a symmetric integral, and it's just going to be 0. So this imaginary part is going to vanish, and the solution to our original integral I, which is this right here, is just pi over e, and then we are done. So that was the complex analysis way. I hope you enjoyed it. I hope I didn't make any mistakes. I just can't do those outros right in the last time. I don't know why. Never mind. I thank you guys so much for watching. If you enjoyed this video, please like and subscribe and recommend me if you like, to your mother, to your newborn son, your newborn daughter if you want. It doesn't quite matter to me. If you want to support me a bit more, link to my Patreon will be in the description. I'm doing all this stuff for free, so I would highly appreciate it if you would, for example, spend $1 on me doing those videos. And up until the next video, have a flammable day. See ya.